All right. Thank you for coming to this lecture today. So today is a bit rainy. It's not an ideal day for lecture and attending the lecture, but thank you. So let me see. Is that going on, right? Okay. So let's start today's lecture. So we will continue analytical digital converter. So now we are approaching to the end, almost the end of this course, Integrated Analog Systems. So as user, lecture 10 video slides are loaded, and you can access the QR code here for later if you have question. And this is a reminder of assessment criteria. So we introduced in lecture 1, right, about this percentage project quiz and CAD exercise. So please note that in CAD exercise, there are some obvious grading, the point that, for example, if you correctly write down the report general requirement, then you get 20 point, something like that. That will be also taken into account for fair comparison with the quiz. And also project, we have 40%. And the CAD exercise 9 will be announced this weekend. So please submit a report for about CAD exercise 9. This is the last CAD exercise. So deadline is after the end of the course, the lecture. And you will have extra more days because CAD exercise 8 is also ongoing. So you can allocate more time. And CAD project. So details will be announced soon. So the target about CAD project is make use of everything you have learned in this course and design and verify an analog integrated analog system of anti-aliasing filter plus ADC. So you can freely choose any architectures that satisfies the specification. We will provide and announce what specifications are required to meet. And teaming up is encouraged, so maximum 2 people. But it's not mandatory, so if you want to, yeah.
Will this include layout or?
Oh, no layout. No, we haven't gone through any layout in this course. But yeah, that's also a very important part of our integrated circuit design. So probably by next year, then we can consider including layout. Yes. But for this year's course, there will be no layout, so only schematic. And possibly the theory comparison to theory for running MATLAB or Python script. And this is a reminder as we talked about last week. So 20 points by completing the end of survey, end of the course survey. So this is equivalent to a perfect quiz round score and anonymous and opens in, I think it was mentioned to open in 1 week. So probably this week or next week it will open. So what we're going to run in this lecture today, lecture 11. So we will review the nonlinearity matrix of ADC. So there was a small mistake in the last lecture about the equation of the DNL. So it might have been a bit confusing to follow, so I will go through again and understand the quantization noise in ADC. Understand the performance matrix of ADC, and we will go through CAD exercise 7. Okay, so this is it for today's outline. We will have quiz solution for ADC part, nonlinearity, quantization noise, and performance metrics, and we will have a CAD exercise walkthrough session. So this is a quiz 8 score. Yeah, you can see that it is quite a nice job. Many of you have scored more than 10 or even more than, higher than 15. So this is, again, this is excluding students who did not attend the quiz, which is good. Yeah, here, quiz 8 retake. After retake, you can see that average is over 15. And this is a quiz 9 score. So I still believe that this is quite nicely distributed. Here, the average mean value for the score is 10.6 and is quite nicely distributed Gaussian distribution. And I heard that this was a bit challenging not a bit very challenging last time. So let's go through it for quiz 9. And yeah, this is a quiz 8 retake questions. So here we have switched capacitor filter, and we have went through and introduced what is the Z-domain transfer function of this switched capacitor filter. And let's derive the DC voltage gain of this filter, justify your mathematical calculation. So for this, this is quite straightforward, I think, because we have gone through last week about how to solve DC gain or DC condition, right? For getting DC gain, you can simply plug in S equal to 0 here, then Z becomes 1, and you can just plug into Z equal to 1 into this Z domain transfer function. Then you get this C1 over C1 plus C2 and 1 over. So this G to the power of minus half becomes 1, and G to the power of minus 1 also becomes half. So by just doing some calculation, you get gain is equal to 1, which is obviously true because there is no active components. So this is a passive low pass filter. Substituting S equal to minus omega p. So here minus omega p, it means that, if you remember, this is a S domain. We have sigma and j omega. And for the first order low pass filter, there is a left half plane pole here, right? And we call that this is a region of convergence, right? And if there is a pole on the left half plane, then we call that the system is stable. So we can substitute S equal to minus omega p, because now we have a left half plane pole, and let's assume that we have it, which is true because this is a stable system, first order low pass filter. Then simply you can calculate what is the continuous time equivalent pole frequency. So you get, first of all, you get Z domain pole here, which is equal to C2 over C1 plus C2 here. You can simply make denominator equal to 0, then you get pole. And e to the power of S equal minus omega p, Ts, then you get this equation. Solving this equation, then you get this. Omega p is equal to Fs times Ln, this equation, C1 over C2 over C2. And the last question, last sub-question of question 1 is that the core idea is this. So we calculated the accurate pole frequency of this transfer function, and can we approximate from here to a bit less accurate, which is excluding the effect of C2 capacitor, just modeling this C1 and switches as 1 over FC, right? That goes to switched capacitor resistance. And when we derive it, then we get Fs or C1 over C2. So can we go from here to here? Yeah. So this is the question. So, and then the last part of question 1 was just to prove that we can go from here to there and use these mathematical expressions. So it is quite straightforward. You can match this Ln, internal term of Ln. Then you have to first make sure it is form of A over A plus B. So you take it out as a minus. This is a Ln, right? Then C2 over C1 plus C2, and then you make 1 minus B over A plus B. Then you get this, and assuming that this term is much less than this term, then you can approximate ln 1 minus x as minus x according to Taylor approximation. Then you calculate the Fs C1 over C1 plus C2, and finally applying C1 is much less than C2, then you get this Fs C1 over C2. And the second question is non-overlapping clock generator. So this question was just follow this structure and calculate how will logic on stage be changing. So let's assume that clock is 0 at initial condition. Then here clock is 0, that goes to here 0. And if this is 0, then the gate output becomes 1 and 1, and V2 becomes 0. And going through the inverter, then both of NAND gates are 1, right? Then the output becomes to 0 and 0, and the V1 is 1. So this is the initial condition. And let me see. Okay, so the first sub-question is that let's assume that clock transitions from 0 to 1. Then you can simply plug in from 0 to 1. And this is exactly how we studied and how we have seen during the lecture slide. 1 to 0 going through the inverter. Then NAND output becomes to 1 because one input terminal becomes to 0, right? Then goes to 1 and it goes to 0. So now the NAND gate, both of our inputs are 1. Then this one goes to 0, this one goes to 0, this one goes to 1. Such that the transition travels to this direction and makes the V1 goes high first. And then that transition travels here, and there are some delay elements through the buffer. So this is the first process. This is the second process. Then the V2 makes transition. No, sorry, V1 should move from 1 to 0. 1 to 0. Then V2 now becomes from 0 to 1. It goes like this, and the time delay between those transitions at the output, now it is a delay of the buffers, 2 buffer stages. So that was the question. And this is the true reason why there can be always a dead time or non-overlapping period. Yeah, the circuit element responsible for creating this non-overlapping interval is because of 2 buffer stages, the delay. So this is a question 9, quiz 9, question 1. So now we have an n-bit ADC has a full scale range. The full scale range is reference P minus reference N. And the reference P is 0.9 volt, reference N is 0.1 volt. So determine the LSB size delta for a 4-bit ADC. This is quite straightforward. You can just simply plug in LSB is equal to this full scale. And we have to divide this full scale by the number of output digital codes, 2 to the power of 4. Then the 0.8 divided by 16, it goes to 50 millivolt. The second question, how many quantization thresholds? This is also quite straightforward because we have 16 levels, 16 digital codes. To make sure this happen, we have to get 15 thresholds. Then you get 16 output codes. So remember, when we have 1-bit ADC, if there is a 1 threshold, then we get 2 output codes. Then assume that the ADC input signal swing is limited by a unity gain buffer whose output range spans only from 0.21 volt to 0.69 volt. So this situation is drawing that here. This is almost this is a 0.7 volt, but our input swing doesn't touch 0.7 volt. And this is a 0.2 volt, but our input swing doesn't touch, the lower bound of 0.2 volt. So this is the situation. Then because our LSB is only 50 millivolt, and this is 0.1 volt, which is reference N. And here we have 0.9 volt, which is reference P. So in this case, this area and this area, we are not using it at all because our input signal is only swinging from 0.21 volt to 0.69 volt. Then the question is how many output digital codes are there that we are actually using. So calculate it. So the question was for calculating this area, that was quite straightforward, right? Because we have reference N, 0.1 volt, and we have 2 times LSB. If there is a 2 times LSB, then it goes to 0.1 volt. So summing up together, we get 0.2 volt. So there are 2 output codes. So 2 unused codes. And for 0.7 volt, from 0.1 volt, which is reference N, plus 12 times LSB steps, then you get 0.7 volt. So 15 millivolts times 12, it goes to 0.6 volt. So that means this range, there are 12 output codes, right? So substituting each other, then you get finally there are 10 output codes that you are actually making use of it. Of course, you can let me erase. You can manually draw this kind of labels for 16 output codes, and you can count manually how many codes are there. But this is only possible if you have like 4-bit or 3-bit ADC. But if you have a 10-bit ADC, then there are 1024 output codes. Then you cannot draw manually each time. So it'll be helpful if you design ADC to get used to of this kind of process of thinking. The last sub-question of question 1 is that a designer claims that increasing the ADC resolution from 4-bit to 8-bit will solve the code underutilization problem. So I identified in previous one. So explain whether this is correct. The answer is this is non-correct, right? Even if, for example, even if there are more output codes, so we are adding 4-bit such that there can be more fine threshold. There can be more fine threshold, of course, and there can be more threshold and so on and so forth. But it doesn't solve our underutilization issue because in the end, this is our input range. No matter how good resolution it is, we cannot use this area because our input range is still very small swing. So that is the reason why this increasing bit resolution does not solve the underutilization issue. So the answer is if you increase reference N to high value, if you decrease reference P to low value, then you can make better use of input signal and swing. That's the reason why we use reference P and reference N as we studied in last lecture. And the second question is this. So we have transmission gate and we have on resistance of NMOS transistor, on resistance of PMOS transistor. And let's say designer uses a complementary switch, transmission gate switch. And we have threshold voltages 0.3 volts for each. And let's say we can define this mu and C oxide and width over length for NMOS, for PMOS as alpha and 3 times alpha. So alpha is PMOS case, 3 times alpha as a MOS case, let's say it. Then find the input voltage, where R on N equals to R on P. Then, yeah, you can just solve this equation. So just assign this part as a 3 times alpha, and gate is clock should be 1 to make sure MOS switch is on. So clock is 1 volt, then, and the source voltage is input voltage, then VGS is 1 minus V in. And for PMOS case, we have to drive clock bar here, gate as a 0 volt to make sure PMOS is open. PMOS transistor is switched on. Then VSG is the source is in, gate is 0, then you get V in minus 0.3 volt. And the coefficients are alpha and 3 alpha. And just making, each sides are equal, then you get input voltage 0.6 volt. So the next question is this. On the axis below, quantitatively sketch R on N and R on P parallel as a function of input voltage and in the area of this. So there is no kind of exact tick marks. So you can just very roughly draw it and see what happens. So when you calculate parallelized resistance, you can just calculate from here and then make it parallel and you get it. Then this is the final equation, 2 times alpha, 0.9 minus input voltage. Then this looks like quite similar to 1 over x graph. So let's build fx equal to 1 over x. Then this is how it looks like, 1 over x graph. And for fx equal to, f minus x, then it goes to 1 over minus x. So that is the situation where we flip against y-axis for the minus x case. Of course, there can be other part, the negative part, but we are not considering it because the resistance cannot be negative in your real life. And then finally, if you shift, let me draw it here again. If you shift your function with the coefficient amount of A from here to here, then you get this. So this is quite similar to the formation of 1 over A minus X. And the coefficient here, this is just a multiplication of some coefficient. So you can ignore it because we don't need to draw exact values. So the answer will be like this kind of similar form. So here, the parallel resistance can have increasing function, and the minimum value is definitely within this range. Minimum value is achieved at threshold voltage P. And from part 1, this is a 0.6 volt. For R on N equal to R on P. Okay, so now we have the next question. In a bootstrapped sampling switch, a capacitor CBT is pre-charged to VDD during the up phase. And parasitic capacitance C parasitic exists across the gate source terminals of sampling transistor, initially discharged to 0 volt. So this is a bootstrapped switch question. So we have capacitor here because of gate to source voltage. Gate to source MOSFET transistor. And during up phase, what it means is that this is discharged to Q parasitic is discharged to 0. So this is how it looks like, 0 volt. And so let's follow this equation and the situation. To make sure this is turned up, then this must be equal to 0 volt. That means we are driving MOS gate as a 0 volt. That means we have to switch on those MOS transistors. And if X node is 0 volt, then this transistor is turned off because those are all NMOS transistors. And to make sure NMOS transistors are turned on, we have to make sure clock is 0. That means this NMOS transistor is also off. And if clock is 0, then this PMOS transistor provides VDD. Let me erase it. So VDD to this PMOS transistor, then this one is also turned off. Such that it is providing to 0 volt and clock bar is 1. That means this CBT is charged to VDD, right? This PMOS is turned on, this NMOS is turned on. So this is a VDD, and this is a 0. So initial charge for the CBT bootstrapping capacitor, it is charged to C times V, which is CBT times VDD. So using the charge conservation law, during the off phase, we can calculate parasitic capacitance has a 0 coulomb of charge, and the bootstrapped capacitor is C times V, which is CBT times VDD. And during the on phase, then CBT is connected in parallel with C parasitic here. So it is now connected to here. This is how it looks like. And the bottom plate is connected to input voltage. So this is the situation that it goes to parallel to parasitic cap. Then now we can also apply Q equal to CV. So C is CBT plus C parasitic times VGS, gate to source voltage. So by making charge conservation law, we can simply derive this charge is equal to the summation of previous charges. Then you get CBT plus CBT times VDD. Then VGS is equal to CBT over CBT plus C parasitic times VDD. And to make sure our gate source voltage is higher than 0.9 VDD, then yeah, so you can just make sure here this is larger than 0.9. Then finally you get bootstrapping cap must be 10 times parasitic cap, at least. So the last question is, based on your sketch from part 2, explain why this bootstrapped switch produces less distortion. So this is the case of bootstrapped sampling switch. Then if you apply CBT is much larger than C parasitic, then this one is approximated to VDD, right? Because this denominator part is approximated to CBT, then it goes to VDD approximation. And on resistance of NMOS, then VGS is, we can make sure VGS is almost approximated no matter how big is our input voltage, then VGS is always constant, then R on doesn't change over input voltages, changes. However, in our transmission gate switch case, then on resistance can fluctuate according to input voltage changes. Of course, in real case, you can try to make sure to match like this by properly sizing NMOS transistor and PMOS transistor, but still its resistance value is always higher than the bootstrapped sampling switch, because we are now driving VGS as the maximum value, which is VDD. So this is, in most cases, bootstrapped sampling switch is better in terms of less distortion. But you don't need to write down this kind of much detail, but the question was checking whether you really recognize this difference of transmission gate switch and bootstrapped sampling switch. Okay, so let's go on to nonlinearity, part of ADC. So I couldn't manage to talk about all of these in previous lecture. So on the left side, we are looking at the case of monotonic ADC. And the right side, we are looking at the case of non-monotonic ADC. So monotonic or non-monotonic means that if input is higher than previous input, for example, then we also expect output is higher than previous output. That is the monotonic case. So in monotonic system, input-output transfer curve characteristic must be always increasing curve. However, in the right side, we see that non-monotonic case is that even if input is higher than, for example, here, then the output digital code sometimes becomes to lower than this one. So we don't want this kind of non-monotonic case. So it is also not straightly always going up in terms of transfer curve. So that we call non-monotonic. So this kind of situation can be critical in digital control applications. So for example, let's say we have a battery charging situation. Then we have a cell phone battery, and we have very simplified structure. Let's say we have charging current control. And charging current here, it means that we can control the amount of charging current from our outlet. And we have battery voltage, and let's say our ADC measures the battery voltage in analog to digital. And let's say D out represents output digital codes of ADC. Then based on this D out, let's say we are controlling the charging current amount. Then if our battery voltage is low, then of course we want to charge our cell phone. Then of course, and also we want to charge our cell phone as soon as possible. Then high current is needed as a customer need. But as we go the higher battery voltage, then we don't actually we stop pouring more current or higher current, because otherwise it can make damages to cell battery. Otherwise, it can also cause overheat, because there is a limited capacity of battery. Anyway, if this can happen, for example, non-monotonic control case, then let's say even if battery voltage is high, but the charging current must be also increased like this. So here, our charging voltage is high, but still the output code is less than previous, charging voltage is less. Then the controller thinks that, okay, maybe something is happening, drawing the current this side. So we want to make sure this battery voltage is maintained. Then it can also increase the current amount, very large amount that can cause some unprepared situation. So this kind of monotonicity is important for digital control applications. And this is a recap of ADC linearity. In previous lecture, I explained the concept in a correct way, but there was a mistake on DNL equation. So this is a correct equation of DNL. So we are measuring the width of each staircase, here rear and ideal. And we are taking the ratio of how much this rear staircase width is deviating from ideal. So for ideal case, in each staircase, width have a 1 LSB width in each staircase. So in this case, because rear ADC's width and ideal ADC's width are exactly same each other, right? So in this case, we call DNL is 0 LSB. And for calculating DNL, you can simply calculate, take the ratio and then subtract by 1. Then you can calculate DNL. So for the next case, on rear ADC, we have 30% narrow width. For example, here I draw the 30% narrow width. then we call DNL is minus 0.3 LSB because it's 30% narrower. For the next case, this is the ideal step width, but this is 40% wider. Then we call LSB is plus 0.4 LSB. DNL is 0.4 LSB. And in the next case, our rear ADC is staircase width is 30% narrower. Then we call DNL is minus 0.3 LSB. And you can calculate and so on and so forth. And you can also plot this kind of graph, INL and DNL. So for INL, as we studied last time, INL is just a cumulative sum of DNL. So for instance, for the INL at code 100 here, you can simply just add them up all together, then you get this. This is how the INL is meaningful. Or you can also approach this this method. So you take the previous INL and get the current DNL and make summation. Then you get also this INL value because previous INL value already has a history of previous accumulative sum. And there is also one concept we call missing code. So this happens when DNL is less than or equal to minus 1 LSB. Here we have a red curve. DNL is minus 1 LSB. So if DNL here, this is a situation that we had minus 0.3 LSB, right? Which is 30% narrower. But what if this narrower, and then in the end, it is almost like there is no width at all. Then we call DNL is minus 1 LSB. So if there is no width at all, then there is no such a situation that analog input can obtain the output digital code 011. So there is a missing code. And if you design analog to digital converter or digital to analog converter without much thinking of the mismatches of analog components, then after you measure the chip, this kind of situation may also happen. So this is an important concept for measuring the linearity. So how other people and other researchers are reporting in terms of ADC linearity is this way. So this is an example of 10-bit ADC. So here we have 2 to the power of 10 minus 1. So we take minus 1 because we are counting from code 0, not from code 1. So code 0 to digital code 1023. So there are 1024 output codes, which is a 10-bit ADC. So in this case, we normally report or measure our ADC linearity, the DNL, maximum value of DNL. When we take the magnitude, we get the maximum value. So then we get 0.9 LSB, 0.6 LSB. For the INL, we also take magnitude, which is absolute, and take the maximum. Then we measure, okay, this is maximally deviating from ideal ADC case. So you can see that it is very nicely distributed and very linear ADC for 10-bit. Okay, so by this moment, we can have a short break for 5 minutes. And we will continue our discussion at 8:58. All right, so let's continue our discussion. Don't worry, we will have a CED discussion session. Let's continue discussion during that session. Okay, so let's continue our ADC discussion, quantization noise. So we have run this kind of graph, curve, and I would like to continue on this. So we learned conceptually what does quantization mean. So by the way, I specifically drew the curve like this way. So code 000 actually representing in the middle point of each code range. So if you convert digital value back to analog, then this may also touch 0 volt. So that goes to, it will be going like this. But in this case, for the sake of better understanding and of the initial gearing of what does ADC is going for, I specifically draw this way, such that all the analog values in this range are converted to 0, 0, 0. And the expectation, I mean the average value will be the middle point. So this is just a conventional drawing, but it doesn't mean that a digital output code must represent in the middle voltage of analog voltage. So anyway, so it converts continuous input to a discrete level. So this process inherently involves error. This is obviously, this is very obvious you can think about, right? Because let's go back to elementary school life. Then quantization is just applying rounding for analog values. So we have threshold, let's say 2.5. Then we have value 2.3. We round it to 2. For the value in the middle of 3 and 2.5, in the middle of the value, then those values are also converted to rounded to 3. Of course, the values in the middle of 3 and 3.5 also rounded to 3. So anyway, there are certain thresholds and there are certain quantized values. So that is very similar to what we call in rounding, and we also already learned about this effect in elementary school life. Then the question is how much error it is. So the quantization error we can define as an analog input. So this is a true analog. And if we subtract the quantized value, which is less accurate, then you get the error. So you can take the difference between analog and quantized, let's say digital value. Of course, after quantization, there can be some application or other circuit research. The time domain is not sampled at all. Then we cannot call this one as a digital, fully a digital in our course, but let's say quantized value. Then you can see that the error, quantization error, is actually bounded within plus minus LSB over 2. So now you can see that once the analog value goes over the threshold, then it changes to the next value. So if you can make analogy, the maximum error for our applying rounding is actually bounded within 0.5, right? The error is bounded for 0.5. It's very similar, 0.5 times LSB. So the errors are all bounded within this range. Then the question is, for the certain amount of input voltage, then where will be the quantization error? So we cannot, we cannot judge in priori. So we can only see how much error will be after measuring it. So for example, it can be here. The quantization can be, quantization error can be here, or maybe here. So we don't know it because our input signal is fully random. So in circuit designers and mathematical analyzing people, the people and also we can try to model this process using probability. So you can simply think that in each levels, there are some probabilities. Then will be the probability function will be like this. So, well, we don't know the exact error at any given sample or at any given voltage, but we can bound it within plus minus LSB over 2. So in this case, we model this error in other term, quantization noise or Q noise, as a random variable, such that it has probabilities in each levels of errors. And this we call probability density function. You probably have learned it. What is it? And the area of PDF is actually equal to 1. So our width of this error is actually delta. And if we take the height as 1 over delta, then the area under this curve is equal to 1. And this quantization error is uniform distributed. So it can be in any cases, right, our analog voltage is truly random, then it can be here, it can be this voltage, it can be this voltage, or it can be here and here. So every single, levels of quantization noise, or let's say every single values of quantization noise can have an equal probability. And we model this quantization error as independent of input voltage, or there can be input current, there can be input capacitance. So let's say in generic analog value, we call as input voltage, let's say. Then actually, this is not strictly sense of true, because our quantization noise is somehow related to input voltage. But we try to model it as independent of input voltage. So in mathematical or block diagram wise modeling, we draw this way. In circuit analysis, we have X as an input, Y as an output, and we add error after quantizing. Then we call quantization error as a EQ. Then, if you remember how we analyzed noise in previous Basics of IC Design course, then we get power of our noise. Because the noise, many cases, noise has a certain amount of mean value. If we just take the average, then all of the AC components are just averaged out, and we just face the situation noise is zero. That's not true. So we have to calculate the power of the fluctuating the noise. Then calculating power, you can just simply take the the quantization error square and take the integral over this area. So we have a probability which is height. So we take x squared times 1 over delta, and dx. Here x is equal to eq. So x squared integral, you probably have run it during your high school life. So x squared is 1 over 3 times x to the power of 3. Then you take the integral, then you get this. Delta squared, SB squared over 12. And for calculating the RMS value of quantization noise, you can simply take the square root of power value, which is average power. So it should be average power, but let's say quantization power domain. Then it looks like a bit complicated to show in a very simple format. So sometimes we write or depict this the parameter with a simpler format, which is sigma q. So after taking the square root, then you get delta over square root 12. And remember, the delta we have already studied, which is full scale voltage over 2 to the power of n in ADC. So in this case, then it is also possible to calculate what is the maximum achievable signal to noise ratio. So is this the first time you have heard about SNR? You have no, it is the first time, or
no, it's not first.
Not first time, right? Okay, good. So good. So SNR, we can calculate the output SNR of ADC with the maximally achievable SNR. So for the signal part, let's say we are applying sine wave as a classical analysis method. Then for the sine wave, we can calculate similarly for the RMS value. For the RMS, we can calculate RMS's definition of the definition is this: taking square root, taking average, and taking the square, then you get RMS value. For the sine wave, you can simply calculate RMS value taking the amplitude, which is peak-to-peak value divided by 2, and then you take 1 over square root 2. Then you get RMS value. So now you both have signal and quantization noise. Then you can just simply take the ratio. So so before we go there, let's assume that our full scale voltage is equal to Vref. Of course, the full scale voltage doesn't always be equal to Vreference. For example, there can be some like VLab N, as we studied in quiz, but let's not think about it. For simplicity of calculation, this is the maximum utilization case. So then we can assume full-scale voltage is equal to reference voltage. Then you just take simply ratio. So for taking ratio and calculating SNR, it is important to stay in power domain. So power domain, I will talk about it later, why it is important. So power domain, you can think about this power domain calculation because in previous prerequisite course, BT IC design, we use the power domain calculation for analyzing noise. So anyway, so taking the power domain ratio, then you can end up to simple equation like this. 2 to the power of 2n times 3 over 2. So after deriving the log domain representation, then this is a power domain. You take 10 times log. If this is a magnitude domain, without power, then you take 20. But in this case, we are taking power. So 10 times log 10, you just plug in this value into the log. Then you get very, very famous equation in ADC area, which is 6 times n plus 1.76. So this is an equation. And we call SQNR, which is the theoretical SNR limit of an n-bit ADC. So this means that no matter how good your ADC design skills or no matter how genius you are, you cannot go over this limit. That is the meaning of this equation, dB scale equation. So this is a theoretical limit of uniformly sampled and uniformly quantized n-bit ADC. And this is an example of back to our lecture 1 example of microphone interface. By using this equation, you can very simply calculate what will be the theoretical minimum detectable input voltage for this ADC. So just put these numbers, 10-bit ADC and full-scale voltage 1 volt, and simply calculate it, then you get this 282 microvolt RMS. So after quantizing the ADC input analog to digital, there will be quantization errors, and those errors are here, 282 microvolt RMS. You cannot detect smaller than this. That is the theoretical meaning of ADC. So let's go to the performance metrics of ADC. So this is a time domain transient waveform, and I also take the FFT in Cadence Virtuoso, then you get this FFT output. So I applied analog input, 9 kilohertz, close to 9 kilohertz. There are some fractional digits. I will talk about it later. And we are sampling our analog signals at 1 megahertz clock frequency, and we are also quantizing with 8-bit ADC. So in this case, I took full-scale voltage equal to 1 volt. Then I learned FFT with the rectangular window, and the number of FFT samples are 2 to the power of 11. So in this case, you can see that as we discussed many, many times in this course, we have aliasing when we take the sampling. Then any frequency component after this sampling frequency will be aliased back to our signal band. So in this case, we can just simply plot FFT until Nyquist frequency, Fs over 2. That is the meaning. So even if you plot 600 kilohertz, 700 kilohertz, it will not be good. It will not make sense that much good, because it will be just mirrored images of 500K as a minimum, middle point. So after adding nonlinearity, so what I did is that I just used the idea here. In this case, I just used the idea ADC, idea DAC, and this is an output domain waveform which is analog mapped from ADC output, digital to analog mapped. And I also added one transmission gate before we quantize to analog to digital converter. Then you get non-linearity, as we discussed. Then you can see that compared to this case, now this red curve will become to black curve. Then you can see that there are some spurs, right? Those are all we don't want. And those are added because of non-linearity. So we call distortion is added. And here, what I want to say is that this is a signal component that we are applying close to 9 kilohertz. Except for this signal, and except for DC components, here we have a DC offset, 500 millivolt. Except for DC, except for signal, everything else are noise. That is how we analyze our ADC spectrum. This is the same, except for signal, except for DC, everything else is noise plus distortion. So we have a noisy and we have a distortions, which is our spurs here. And now, as we studied in Basics of IC Design course, if we add more circuits, then there are also circuit noise, thermal noise, flicker noise, and so on and so forth. So compared to here, now you can see that the floor level is increased because of the noise. And the situation is the same. It doesn't change. It has a signal and DC offset. Except for signal, except for DC, everything else is noise, distortion, and those are all we don't want in either case. So this is how we analyze. Oh, sorry, there is a typo. So SQ and R. So for SQ and R, we take the power ratio, then you calculate it, this 6 times n plus 1.76 dB. Then we call signal to noise and distortion ratio, which is normally called SNDR. So now we are adding all the noise and distortion and circuit noise and so on and so forth. So we have quantization noise, which is PQ. We have circuit noise, which is PN. We have a distortion, which is PD. So those are actually random process, except for distortion. Those are random process. So we must add in power domain. We must not add a magnitude domain. Then it will cancel out each other. So we must add power domain. And then we take the ratio to signal power. Then let's say we are applying the same equation because it is very hard to analyze everything in theory. So let's model this one as a N real, the new resolution of ADC. Then there was also mistake here. This one is 1.76, and this one is 6.02. So we call this N real as an effective number of bits, ENOP in short. So we call this kind of ENOP as a modeled resolution. What is the effective range we can actually make use of it out of this ADC? There will be quantization noise, there will be distortion, there will be circuit noise. Then what is the really usable effective numbers of bits? So you can just take simply SNDR minus 1.76, and you can just divide by 6.02, then you get this ENOP. And the dimension is bit. And this is a very typical measurement result you can find from research papers. So you basically sweep for measurement of SNDR and SNR. Here, SNR is calculated without distortion. So for calculating SNDR, there are FFT bins, right? Those are all digital output values, and each frequency bins you have values. So you take signal, you take DC, and everything else are all we don't want. We just simply add them up in power domain. So what it means is that we cannot just add dB scale, right? That dB scale addition means it's just multiplication. So first you need to do is, for example, here, let's say this is a 1 bin. So it's almost like, let's say this is minus 60. Then first you need to do convert to power domain, minus 60. So convert all of these FFT results in power domain and add them up and take the ratio. Then you get SNDR. So for getting the SNDR and plotting over various ranges of the wide ranges of input amplitude, you get this kind of curve. So for low amplitude, this is a small signal region. Then we can apply Taylor series approximation. But as you increase signal input amplitude, then it starts to be distorted because of the nonlinearity of circuit. So at high input amplitude region, we call this as a nonlinear region, and you can see that SNR, SNDR has a difference. So this is caused by a nonlinear behavior. And here, what dBFS, it means that how many deviation there are relative to full-scale voltage. So for example, as we defined in previous example, let's say our full-scale voltage is 1 volt. Then minus 6 dBFS, it means 0.5 volt. Just a half. Half means minus 6 dB, right? For minus 20 dBFS, it means 0.1 volt. 20 dB is 10 factor, right? So you can derive this kind of plot. So before we end the actual part of our lecture, one final note I want to introduce is this. I mean, why not we apply just 9 kilohertz? Why not we apply 10 kilohertz? Why there are so weird fractional digits, like 9.27734 kilohertz? So let me explain why we have to use this kind of odd frequency when analyzing ADC. So this is a concept we call coherent sampling. So for taking the FFT, it is important to match and align for running the FFT or DFT, discrete Fourier transform. But when we take a number of samples as 2 to the power of n, it becomes to FFT according to how we calculate or compute DFT. So anyway, compare the left case and right case. For the left case, the start point and end point of the samples perfectly align each other. So it can continue, model such that the signals are continuously, going on when we just copy and paste, and we analyze. That is how we analyze in DFT domain, right? We assume that the taken samples are periodic. So we just copy and paste, and then that's how it is analyzed is DFT. For this condition, we have to make sure number of FFT times a sampling period here, this time, is equal to integer numbers of input frequency. So it should be met to make sure this kind of situation can happen. On the other hand, if starting point value does not align with the end point, then you can see that there are distortion. This is some sort of different distortion how we measure ADC. So let's say it is not integer, like 1.84. Then there is a spectral leakage. So we call this kind of phenomenon as a spectral leakage. So you can see that it has a kind of skirt shape because of this unconnected continuous assumption. So this is one assumption we have to make sure. And another is that this, as we have seen in lecture 1, we have played aliasing demo by changing rotation per second and under the frame per second a certain amount, right? Then you have found out that when we somehow align this frame per second and rotation per second as an integer relationship, for example, times 4. Then this is, of course, just one moment is captured because I just took the screenshot. But when you run this LS demo, then it will be like this. Rotating and pointing only 4 points. This is because somehow rotation per speed and frame per speed are aligned with exactly 4 vector. Then you can see that within the waveform, there are 1, 2, 3, and 4. Only 4 values are existing that is touching around. So even without doing quantization, you can see that after sampling, there are only 4 levels, which is like without doing any quantization, it looks like only 2-bit ADC. But this is not prepared way. So uppercase is exactly aligned to integer numbers of the input frequency to the sampling frequency relationship, and the lower part is slightly different value was chosen, such that all the sampled values are pointing at in different levels. So what it means is that, let's have a check. So each samples are pointing at the same level, the same value. But in this case, this value, and these values are slightly changing over time. So we want this kind of situation. Otherwise, it will just, by means of sampling, it will look like inherently quantized already. In both cases, M cycle is met as an integer. So how can we make sure this can happen? Mathematically, the proof is out of scope for this course. If we set M cycle as a prime number, for example, prime number means that 3, 5, 17, and so on and so forth, then we can make sure this situation can happen as much as possible. So it does not touch the same values over FFT. So by rearranging this equation, then you get this. Input frequency, sampling frequency ratio is M cycle and number of FFT bins. So in coherent sampling, we call this concept as a coherent sampling. We make sure M cycle is a prime number. And CAD exercise 9, you will go through how to simulate and how to run applying this concept to ADC or FFT spectrum design. Sorry, verification. So anyway, this is a reference.